Hello everybody, welcome back to our last session for today. My name's Anne Peaston. I'm a clinician working at the University of Adelaide, and I'm really pleased to hear from Nicholas Clark and UQ about this particularly interesting study on forecasting canine tick paralysis. Nick is a quantitative ecologist, which is a category of person I had not heard of until last week. And I'm really looking forward to hearing what you have to say about modelling tick paralysis in advance.
Thank you very much, Anne, and thanks very much to everyone on the VetCompass team for allowing me to present. My name's Nick Clark. I work at UQ as an ARC DECRA Fellow, and I'm presenting some work that my colleague Sahil, Arora, and I have been working on to try and ascertain historical cases of tick paralysis from VetCompass data and to build models that can hopefully generate some forecasts for the coming tick seasons. Before I start, I'll just take a moment to acknowledge the traditional owners of the lands that I've been using to do this work and that we're all meeting on today. So the main theme of my work generally revolves around the use of forecast models to try and improve decisions. And that's a very broad sort of field, but ultimately it encompasses, if you think about it, any decision that we make, any decision we make about what we think is going to happen in the future helps to inform what we're going to do. And that's usually based on some analysis that we make of the past, whatever that analysis tends to come from or what kind of form it may take. And in today's environment, obviously, we're working in a sort of big data era where we're collecting more and more data, but it's not just the size of the data that we're collecting, but also the fact that it tends to come from many different sectors and resources. So we're working with large multi-structured data sets. And so if we want to try and use these large data sets to synthesize information to make decisions, it can be very challenging. And so we need tools to be able to make use of large, and sometimes very complex data structures. So this is the main focus of this particular work. Most of you in the vet field will recognize this parasite. This is Ixodes holocyclus, which is the main paralysis tick in Australia. And it's responsible for, we think, many thousands of admissions to veterinary clinics each year. And what you're seeing rolling across the screen is just some of the sort of sensationalist headlines that we're often bombarded with in sort of the spring and summer months each year to warn us about the dangers of tick paralysis. And some of these are reasonably well justified because it can be a fatal disease to our pets, and occasionally it can be quite harmful to humans as well. But ultimately, we don't know a huge amount about what actually drives or what actually determines differences in rates of tick paralysis across years or across seasons or across space. So we know enough to know that rates do differ across different regions, and broadly that might relate to the types of habitats that these ticks occupy and that they use for their intermediate hosts, such as small mammals, for example. But we don't actually know enough to be able to determine, are the changes that we've made in terms of new drugs making a big difference, and what can we do to actually improve management of tick paralysis going forward. So that's the main focus of this particular work, but as you'll see, it'll probably raise more questions than it will answer. So I'm working on one of the projects for VetCompass to actually try and build models of tick paralysis. And so we've been using VetCompass data that on the last count encompasses about 2.7 million different rows, so unique consultations. So obviously this is the same sort of size problem that most of us are dealing with when trying to actually make sense of these data. And so the first aim was to try and ascertain historical cases of tick paralysis. And so what we did was obviously to go into the raw text, which I think most people who've presented so far today have been doing the same sort of thing. So I don't really need to bang on about the fact that the clinical text is obviously very messy and unstructured, but often very useful as well. So here we have a sort of pseudo text that is based broadly on a few texts that I've seen, where we can see lots of misspellings and interesting abbreviations, some of which might be useful and some might not. But there's multiple lines of evidence here that this might have been a tick paralysis case. And so we had to define a way to try and mine through these using algorithms, because obviously we're not going to search 2.7 million rows manually. And so what we did was come up with a bespoke, what we called a veterinary dictionary, where we had to come up with different types of terms that might, or combinations of terms that might all have common meanings. And so we were able to use those to define sets of synonyms while trying to account for misspellings or different combinations or different phrases that veterinarians often use to try and capture any terms that we thought might be important. And this is an ongoing exercise. We keep iterating through this every time we run a new trial of our algorithm. But basically the algorithm works in the sense that we do a couple of natural language processing steps where we tokenize the words. That just means we split them into unique words. And then we operate in an iterative sense by spell checking, pattern matching against our own veterinary dictionary. And then we run our spell check again and re-pattern match. And we do this a number of times to try and capture as many ways as we think some type of information about tick paralysis might be stored in those raw clinical texts. The classification was to originally, at the moment, we're classifying into 3 different categories. The first would be sort of a gold standard where the practicing clinician has clearly treated this as a tick paralysis case, whether they gave tick antiserum or did some other treatments, but we're very confident that a tick paralysis case was found. Maybe they found an actual paralysis tick. The second category is sort of somewhere in between, kind of a probable tick paralysis case where a tick crater might have been found or a tick was found, but it wasn't confirmed as a paralysis tick, as well as some possible symptoms, but no tick antiserum was given. So those are the ones that we're really concentrating efforts on to try and improve. What kinds of patterns are we missing in there that might give us more ability to try and get a better classification. And then the third category were the ones where we're highly confident that this wasn't a tick paralysis case, or at least it wasn't obvious at all to the practicing clinician. And so by operating on the data from, I think from about 2004 is what we're focusing on at the moment, which is sort of the cleanest data in VetCompass that we've found going forward. We've found, I think, 20 or 25,000 cases in the gold standard so far. But again, we're constantly improving our algorithms and checking those using a veterinarian to actually go through and manually check a subset from each category to see which ones are what patterns are we missing there. But it's encouraging that at least the data makes sense to us. This was the first thing we wanted to look at. Does it actually look like it could make sense as tick paralysis? And broadly, if you look at the very top of the screen, the national aggregate is broadly following the kind of seasonal pattern that we would expect to see with peaks during spring and summer and falling away during the wintertime. Queensland cases tend to peak earlier and fall earlier compared to New South Wales cases. And again, that broadly makes sense based on latitudinal variation in the climates. Okay, so that's all really useful information to give us some idea of the kinds of structures that we're dealing with here. But something that was really interesting was to look at the actual individual time series. So we're operating on the LGA level here, which is just a grouping level that gives us access to ABS information, such as population sizes and other census data. So it makes sense to use that as an aggregate level. But we broadly see, cases tending to trial along, some dips over time, and then quite large dramatic drops from around 2015, 2016. I've just highlighted when the sort of latest generation of drugs, the sort of Bravecto and NexGard that we're using as preventatives came on the market. I think they were approved in 2015 in Australia. And it seems that the drop could coincide roughly with that. It's hard to say definitively whether that made a huge difference, but that's something we'll look into. And there are ways to try and actually test whether the trends that were going down would have gone down as much if those hadn't come on board. But we see the same pattern across basically all of Australia, which was really interesting. We weren't expecting to see that. And at first I thought this must be a fluke. So I've really been digging, and it seems that the pattern holds up. And most of the clinicians that I've talked to about this have broadly agreed that since they've been using the latest generation of drugs, they've noticed dramatically fewer cases than they were seeing in the past. So that's quite interesting and an interesting finding here. It's even more obvious if we look at it from a sort of 1 year moving average to try and remove the seasonality. These are normalized, so Queensland tends to have higher cases than New South Wales, at least in the data, but we would normalize them so they're on an even scale there. And again, you can see a dramatic drop somewhere around 2015, but it does look like the drop might have started a bit before that. So it's kind of hard to say exactly how much effect these drugs have had on that particular drop. But either way, the fact that it's very consistent across all the clinics that we've been looking at is kind of interesting and noteworthy, I think. But how to actually make sense of this? So the next step is actually to perform some statistical models on these. So part of my fellowship is developing tools to actually be able to synthesize multivariate and nonlinear discrete data sets like we're dealing with here. And one of the models I'm building is dynamic generalized additive models. You don't have to know much about the way these work. Just know that it's a way of combining nonlinear covariate functions with principal time series models so we can actually generate sensible forecasts into the future. And importantly, both of these terms, both these components can be multivariate, so we can learn from multiple time series at the same time to try and improve inference of covariate effects as well as improve our forecasts. And that's really important when you're dealing with time series that can have very different levels of missing data or different levels of information basically in those series. We want to be able to learn from all of them jointly rather than modeling them individually, which would lead to poor models for some of those uninformative series. And we estimate all these parameters in a Bayesian framework, but again, you don't need to know too much of the details there. I've decided to show one formula. I hesitated whether to do this, but I think it's useful to walk through. It looks ugly at first, but I can walk through what it means. Basically, each time series is a discrete draw Poisson observation, and the linear predictor is basically captures hierarchical variation, so random intercepts across different LGAs. I've just shown one particular model that's being trialed, which is called a distributed lag model, which basically means that we estimate a different nonlinear function for each lag of, say, minimum temperature, and those functions are partially pooled across states. So again, we're learning information across all the different series that we're modeling to try and estimate how minimum temperature might influence tick paralysis cases over increasing lags. So it's a very useful model for this kind of approach. And the final component is just a joint time series model using a dynamic factor process. Just to illustrate what that distributed lag actually does, this just shows the power of the kinds of models that we can use here. So here's just, don't worry about the y-axis here, but basically this is just different values of minimum temperature across Queensland. And this is just the type of curve, the effect that we expect to see across increasing lags going back in time. So it allows us to model the seasonality of the series by understanding how ticks are proportionally responding to increases in minimum temperature, which is how we think ticks tend to work in their biology. You can see that these curves are broadly similar, but they change slowly and change smoothly over time, going back to increasing lags. And then the curves for New South Wales are related, but different again, because it's a hierarchical model, so we're learning both of those jointly. So that's just a bit confusing to watch, I understand, but it's useful to understand how these models can work if you're dealing with time series, which most of us are probably dealing with if we're working with VetCompass data anyway. From an academic standpoint, it's useful to understand different potential covariate effects or effects of interventions on the actual tick paralysis rates, but we're really interested in trying to communicate the results of our models to people who might actually be able to use it beyond academia. And so we've been working on a dashboard where my colleague Sahil Arora has been working quite hard on trying to build something that we can actually showcase the kinds of data that we're dealing with and how our forecasts are working and what we might be able to do to improve those. So we have a dashboard online that we're just hosting on GitHub at the moment, which might be interpreted, or excuse me, and worked into the VetCompass framework eventually. But it just shows, this is interactive, this is just a screenshot, but it's actually an interactive dashboard to highlight different time series and different ways of aggregating and different ways of visualizing the time series. And we also have a separate one for the actual forecast, which takes some information into what we're expecting to see, what kinds of trends we've seen for different regions and different ways of synthesizing that information to try and respect the uncertainty in the forecast, but hopefully in ways that people who are not used to reading these kinds of things could actually make some sense out of it. This is something that's ongoing. Again, we're trying to continuously improve the way we present this so that more and more people can actually use it. So on that note, we have an actual survey that's ongoing, just a questionnaire really to try and understand different people's experience or expectations about how tick paralysis can be managed or how it's trending and what other aspects we might need to consider when building our models or when presenting our forecasts. So if anyone's interested in this, I'd be happy to share the link, or I can pop it in the chat if anyone's interested in looking at it to get a sense of whether that might be useful to them to contribute. Or you can welcome to email me anytime if you have any questions. So I think I'm out of time. On that note, I'd just like to say thank you very much to the organizers for allowing me to present. And thank you so much to the VetCompass team for all your patience, for helping us to get the data together. And I'm happy to take questions if there is any time.
Thank you, Nick. That was really interesting. Has anybody got any questions? I'll kick off with one question, Nick. I don't believe there are any other questions. Are you applying this to other diseases in the veterinary sphere at the moment? This I guess, quantitative ecological approach?
Yeah, that's a great question. I'm sort of tangentially involved in some work on, say, a heartworm, canine heartworm, which would be kind of similar in a sense. So there are a lot of diseases that I think mosquito-borne or vector-borne in general that would have similar kinds of patterns we would expect to see, where you're intersecting one health. You've got environmental components and you've got dog owner or pet owner components and interventions from drug companies. So lots of things going on. So I think the actual framework would be able to be applied to a wider range of diseases. But my main focus is really on getting the whole sort of system together so that we can actually show it from start to finish and then say, well, what other diseases could we actually apply it to? But I think, yeah, there would be many that could work potentially.
I might keep going with another question since I don't think anybody else has some specific questions. Keith, if you have a question, can you pop that into the chat if that's to do with Nicholas's presentation? But in the meantime, Nicholas, I've been reading lately of the influence of drug residues in all sorts of natural spaces. And I'm just wondering whether, so for example, I was reading about the influence of insecticide residues from pet animals on local insect life, or even in waterways on reproduction and growth in fish. And I'm just wondering whether there's any wider application that you're interested in and potentially participating in on that sort of a level.
Well, yeah, absolutely. I mean, I think, again, it's a kind of question that links across, what I call it as an encompassing One Health kind of question. You're thinking about environment and health all at the same time, which I think is kind of a needed approach. So certainly, yeah, I'd be very interested in that approach.
Right. But not doing anything along those lines right now.
No.
Okay, there's a topic for another grant and much more collaboration, no doubt.
Yeah, thank you very much.